Hi Shiny, Senior Physics Faculty from Knowledge Hub. So today we are going to learn more about light. In our first session, we have discussed what is reflection, reflection due to spherical mirrors, reflection on spherical mirrors. So today we are going to learn refraction, right? And also we are going to learn what is absolute refractive index, relative refractive index, and the laws of refraction. Right. So what is refraction of light? In general, we already know that light has a property called rectilinear propagation of light. So light has a property called rectilinear propagation of light. So that means light always travel in a straight line path. Light always travel in a straight line path. So until when it travels in a straight line path? Until it hits an obstacle or enters into some another medium. So we know that light always travel in a straight line path, but till when? Till when it travels in a straight line path? Until unless it hits an obstacle, it travels in a straight line path, or it enters into, if it enters into another medium, it definitely deviates. So this is what we have in rectilinear propagation of light. So for suppose if there is an obstacle like mirror, what happens to this light? So when you have a light ray which is incident on the mirror, you know that if it is incident exactly at pole, it reflects back. It is deviating from its path. But if there is no mirror at all, what happens to this light? It just continues to move in a straight line path. And this is what we know about rectilinear propagation of light, which we have learned in 8th class even. And what about refraction then? So what is this refraction? So light travels in a straight line path until it hits an obstacle like mirror. First, suppose if this light enters from one optical medium to another optical medium, one transparent medium to another transparent medium, light undergoes bending. So light will refract. It undergoes bending, we can say. It changes its direction of propagation, we can say. So this property of light is called as refraction of light. So when light enters from one optical medium to another optical medium, light undergoes bending. So bending of light is refraction. So it is very clear that this is the actual path of light. So but if it is entering from one medium to another medium, it undergoes bending. So why it undergoes bending? Because its speed is changing, because the light speed will be changing. Once it is entering from one medium to another medium, its speed gets changed, and that is the reason why it undergoes bending. So this property of light is called as refraction. So here refraction can be in two different ways. So like how? So see, this is the actual path of light, and light can bend towards the normal. It's very clear that light is bending towards the normal here. First, suppose if light is entering from some different medium, say denser to rarer, in general we say this as denser to rarer. So when light is entering from denser to rarer, it bends away from the normal. So bending can happen in two ways. It can either bend towards the normal or it can bend away from the normal. And these angles are very clear that this is angle of incidence, this is angle of refraction. This is angle of incidence, this is angle of refraction here. So what is angle of incidence? Angle between incident ray and the normal. And what about angle of refraction? Angle between the refracted ray and the normal. The same thing is here. So when does light bend towards the normal and when does light bend away from the normal should be the question. Yes. So it's all about refractive index. So in order to understand why light bend towards the normal and why light bend away from the normal, we have to know something about optical density of a medium. So right. So generally speed of light is more in rarer medium. We have two different media. We have two different types of optical media. Optical media are of two types. One is optically rarer medium and the another one is optically denser medium. So in optically rarer medium, the speed of light is more. In optically rarer medium, speed of light is more. So speed of light is more in optically rarer medium. So light travels fast in optically rarer medium. And in optically denser medium, the speed of light is less. So when light is entering from optically rarer to denser medium, so light bends towards the normal. Its speed decreases and it bends towards the normal. In the similar way, while light is entering from denser to rarer medium, its speed increases and it bends away from the normal. So we have to remember what are different types of optical media. One is optically rarer medium and optically denser medium. In one of the media, the speed of light is more, and in another medium, that is in the first medium, that is rarer medium, speed of light is more, and in the next medium, speed of light is less. So this optical density of a medium. So whatever we are talking about is optical media. That means we are indirectly talking about optical density of a medium. So the optical density of a medium is measured by using a factor called absolute refractive index. So when we are supposed to ask, if they are asking us about what is this optical density, we can explain optical density based on this absolute refractive index. So absolute refractive index is a measure of optical density. It is a measure of optical density of a medium. It is a measure of optical density of a medium. So right, how to define absolute refractive index? So absolute refractive index is simply the ratio. It is a ratio between the speed of light in vacuum to the speed of light in the given medium. So here C represents, it is here the C represents the speed of light in vacuum, and V represents the speed of light in the medium. So first, suppose if you are talking about absolute refractive index of certain medium, if we are supposed to find the absolute refractive index of certain medium, that means we should know the speed of light in that medium. So here V represents the speed of light in that medium. Okay. So N stands for absolute refractive index or simply refractive index. So in order to find the speed, of light in that medium, we should know the refractive index of the medium, and vice versa. So that means if we can able to calculate this absolute refractive index if we know the speed of light in that medium. So right, and when we talk about the units of this absolute refractive index, so this is the speed and this is the speed. Both are measured in meter per second. So there won't be any unit for calculating this refractive index. No unit. It is a unitless quantity. Right. So we'll talk about the C and V ones. So what is C here? It is the speed of light in vacuum. And V is here speed of light in that medium, in one specific medium. So when you compare the C and V, C is always greater than V. And why is that so? Speed of light in free space is around 3 into 10 power 8 meter per second. 3 lakh kilometer per second. 3 lakh kilometer per second. It is maximum. The speed of light is maximum in free space. So once the light is entering different media, its speed gets changed. Its speed decreases. But in vacuum, the speed of light is maximum, and you have to remember this value, that is 3 into 10 power 8 meter per second. So when you compare C with V, definitely C will be greater than V. But first, suppose if you take air as the medium, the speed of light in air is almost same as this value. So that is why we are considering that C is either greater or equal to V. So we just take an approximation that C is almost equal to V. So when we will take C is almost equal to V? When you are talking about a medium called air. Only in that air medium, the speed of light is almost same as the speed of light in free space. This has to be clear. So now if C is definitely greater than or equal to V, then I can say C by V is definitely greater than or equal to 1. If I send this V to the other side, it goes to division. So C by V is definitely greater than or equal to 1. That means this value is nothing but absolute refractive index. So this value is definitely greater than or equal to 1. So absolute refractive index of any medium if you take, it will be either greater or equal to 1. Equal to 1 when we consider the medium as air. Of course, it's not exactly equal to 1, but yes, we'll round it off to 1. So n is always greater than or equal to 1. This has to be clear. And it doesn't have any unit. So refractive index is something based on what we can talk about optical density of a medium. It is a direct measure of optical density. So this also must be clear. This is a direct measure of optical density. Direct measure means, first suppose if refractive index is more, the optical density of a medium is more. If refractive index is more, the optical density of a medium is more. Optical density is more means it's an optically denser medium. It's an optically denser medium. So if refractive index is more, I can say that optical density is more because it's a direct measure of optical density. And if optical density is more, we can say that it is optically denser medium. And similarly, if refractive index is less, optical density is less. If optical density is less, I can say that as optically rarer medium. So in order to talk about refractive index of one given medium, we should definitely know the speed of light in that medium. So if you can able to get this value and you already know what this value is, 3 into 10 power 8, and suppose it is 2 into 10 power 8, then 3 into 10 power 8 by 2 into 10 power 8 gives the refractive index of that medium. So then what about this relative refractive index? So refractive index talks about one specific medium. Refractive index talks about one specific medium's refractive index. Like absolute refractive index purely talk about a single medium. So when I talk about relative refractive index, that means we are comparing refractive indices of two different media. So the representation is either like this or like this. That means these both are different from each other. So based on the requirement, we have to use whether this or this based on the requirement. That means this means that this is the refractive index of medium 1 with respect to medium 2. So we are talking about relative refractive index. So that means two media have to be involved. So this means refractive index of medium 1 with respect to medium 2. So I can write N12 as N1 divided by N2. So again, N1 means what here? It is the refractive index of medium 1, and this is what? This is the refractive index of medium 2. So it's simply the absolute refractive index of medium 1 divided by absolute refractive index of medium 2. So which is nothing but C by V1. We already have the formula for absolute refractive index, which is C by V1 divided by C by V2. So once you cancel the C, you will be getting this as V2 by V1. So that means I can conclude that refractive index of medium 1 divided by refractive index of medium 2 is V2 by V1. V2 divided by V1. So, and light is an electromagnetic wave. We generally know this. While we are learning in the properties of light, we involve that light is an electromagnetic wave. So generally velocity of a wave is represented as frequency into wavelength of that particular color of light or light in that medium. So frequency into wavelength of light in stands for velocity of light in first medium. So frequency of light into wavelength of light in medium 1. So this is wavelength of light in medium 2 and this is wavelength of light in medium 1. So frequency depends upon the source which is producing light. So it will be same in both the media. So F gets cancelled. So finally N1 by N2 is equal to V2 by V1 and that is equal to lambda 2 by lambda 1. So here N1 refractive index of medium 1, N2 refractive index of medium 2, V2 the speed of light in medium 2 and V1 the speed of light in medium 1. Lambda 2 is the wavelength of light in medium 2 and lambda 1 is the wavelength of light in medium 1. In the similar way, we can even write N21 formula. What does this mean first? So this is refractive index of medium 2 with respect to medium 1. Refractive index of medium 2 with respect to medium 1. So I can write this as N2 by N1. N2 by N1. So finally, we will get this N2 by N1 as V1 by V2, and which is equal to lambda 1 by lambda 2. So in numericals, from based on this concept, you may have numericals where they will involve the refractive indices of two media, and they will ask us to compare the speeds of light in these two media. So please be very clear that in the numericals they may give the values of refractive indices of two different media, and they'll ask us to find the speeds of light. They'll ask us to compare the speeds of light in these two media. So that means based on this relationship, we can determine the speed of light. We can compare the speeds of light in two different media. And what about the unit? Yes, again, this doesn't have any unit, this doesn't have any unit. So this also doesn't have any unit. So relative refractive index also doesn't have any unit. And also another important point related to relative refractive index is, so it can take any value less than 1, 2. So its value lies between 0 and 1. It can be less than 1, 2. It can be less than 1, unlike refractive index. And what's the reason for that? See, here it's all about two different media. So let us suppose this first medium is rarer and the second medium is denser. So first medium is rarer and second medium is denser. That means this value is less than this value, isn't it? So the first medium is rarer and the second medium is denser. So the first medium's refractive index will be lesser than this medium. So a small value by a big value becomes a small value, isn't it? So if I take 2 by say 3, this is less than this. So in general, 2 by 3 if I take, it will be definitely less than 1. So that means relative refractive index can be less than 1. If I take the first medium here, in this case the first medium if it is rarer and the second medium if it is denser, this value will be less than this. So the ratio will be less than 1. In the similar way, if I take first medium as denser medium and the second medium as rarer medium, this value dominates this. N1 will be greater than N2, then N1 by N2 will be greater than 1. So it can take the values anywhere between 0 and 1, and it doesn't have any unit. Right. So the important note points are refractive index of a medium is a direct measure of optical density, which we have already discussed that in order to talk about optical density of a medium, in the question if something like optical density is involved, they are indirectly asking us about refractive index only. So refractive index of a medium is a direct measure of optical density, and refractive index doesn't have any unit, no unit. And I have already mentioned if a medium has more optical density, then we can say that it is optically denser medium, and if a medium has less optical density, we consider it as optically rarer medium. So the next point is, second point, absolute refractive index can never be less than 1, which we have already discussed, the ratio. It is a ratio between speed of light in free space to the speed of light in the given medium. So C always is greater than V, or sometimes can be taken as V only when the medium is air. So if you take this ratio, it will never be less than 1. It's always greater than 1. It can never be less than 1. That means N is always either greater than or equal to 1 we can take. So we will take N equal to 1 for air medium in general. You can remember this. So relative refractive index can be less than 1, 2. Yes, as I told. So relative refractive index is a ratio between the refractive indices of two media. So if I take the first medium as rarer and the second medium as denser, this value will be less than 1. And if I take first medium as denser and the second medium as rarer, it will be greater than 1. So air is optically rarer among all the other media. So we generally in questions, most of the questions, they generally compare different media like air, glass, water, and sometimes some other media too. So mostly, in most of the questions we see these, and also diamond sometimes. So air, we almost equate it as 1. Just remember it as 1. That is enough. Refractive index of air can be directly taken as 1. So in most of the examples, the glass, they'll take the glass slab's refractive index as 3/2. Of course, it has some other values like √2, √3 too, but in our 10th class, in some questions, in most of the questions, they use this value of refractive index for glass, and water has a refractive index of around 4/3, and diamond will take the refractive index nearest to 2.42. So if you just check these 4 media, if you just compare these 4 media, so refractive index is more for diamond. See, 4/3 is 1.33, 3/2 1.5. So when you compare the refractive indices of all these 4 media we have, so diamond has more refractive index. So diamond has more refractive index means what about the speed of light? It will be less there. Why? So if refractive index is more, optical density is more. So if optical density is more, we consider that as optically denser medium. Optically denser medium. So if it is optically denser medium, the speed of light is less there. So that is why among all the 4 media, in this 4 media, the speed of light is less in diamond. And speed of light is maximum. When you compare all this, the speed of light will be maximum in air. You can remember this. So among all the media we have, air is considered as optically rarer medium. Right. So this is a doubtful question to many of the students, whether optical density is same as mass density. So no, optical density is different from mass density. So mass density base, we go back to that density concept which you have learned in 9th class. So density is something called as mass by volume. Density is mass by volume, right? So you know that when you talk about kerosene and water, we'll consider an example of kerosene and water. So if you take a container with kerosene and water, kerosene will float on water. So why is this kerosene floating on water? Because of its density. So its density is less than that of water, so it floats on water. But when we compare the optical densities of kerosene and water, like if we compare optical densities, kerosene has more optical density compared to that of water. Just remember this. So mass density is different from optical density. Optical density talks about how well the light can get refracted in that medium, how well light can bend in that medium. But mass density is all about density of substance. Density is mass by volume. So kerosene floats on water because of its less density than that of water. But when we compare optical density of kerosene with water, optical density of kerosene is more than that of water. You can remember this. So optical density is different from mass density. So then we have laws of refraction. So the first law is very simple, which we already learned, something which is very similar to this in laws of reflection. So incident ray, refracted ray and the normal lie on the same plane. See, refracted ray, if I say refracted ray, that means definitely angle of incidence will not be equal to angle of refraction. We know that because light is bending. So we can't add that angle of incidence is equal to angle of refraction, because it's a blunder, because refracted ray itself means light is bending in one particular medium. Light is bending in one particular medium. What? Sorry? Thank you, Soumya. Thank you for the comment. Thank you so much. So Snell's law. So the first law is incident ray, refracted ray, and the normal lie on the same plane, right? So the second law. So in the first law, you have to be very clear. It's very similar to that of laws of reflection. There, the incident ray, reflected ray, and the normal lie on the same plane. In the similar way, in laws of refraction, the first law is incident ray, refracted ray, and the normal lie on the same plane. And remember this, angle of incidence will never be equal to angle of refraction if the light is suffering refraction. If the light is undergoing refraction, definitely angle of incidence will never be equal to angle of refraction. The second law is Snell's law. So in this law, what we have to actually understand is, for a given pair of optical media, see, this is fixed. If you talk about a pair of optical media, for a given pair of optical media, the ratio between sine of angle of incidence, the ratio between sine of angle of incidence and sine of angle of refraction, this is constant. The ratio between sine of angle of incidence and sine of angle of refraction is constant. This ratio always remains constant, but for a given pair of media, this ratio will remain constant, and the value of this constant is refractive index of second medium with respect to first medium. The value of that constant, whatever fixed we are saying, that particular fixed value is n21, refractive index of second medium with respect to first medium. For suppose I take medium 1 and medium 2. So I am taking a light ray which is incident in the first medium, and this is the normal, and let us suppose it is undergoing refraction. So this is angle of incidence and this is angle of refraction. So the law states that sine of this angle by sine of this angle value is always fixed for a given pair of media. And that fixed value is nothing but n21, which is nothing but refractive index of second medium divided by refractive index of first medium. This has to be clear. Right, what does this mean again? So first, suppose if I change the angle of incidence, what happens? First, suppose if I change the angle of incidence, to some other value, proportionally angle of refraction must change. That is the law stating. So if I change the angle of incidence, then angle of refraction also will change in such a way that angle of refraction also changes in such a way that this value sine I dash by sine R dash still remains the same as this value. See, in the before case, whatever angle of incidence we have taken, corresponding angle of refraction if you take, and if you divide, you will get the refractive index of second medium with respect to first medium. First, suppose even though if you change the angle of incidence to some other angle, say I dash, what happens to angle of refraction? It definitely changes in such a way that if you again take the ratio of sine I dash and sine R dash this time, that will be same as sine I by sine R, and that is constant, and that value is refractive index of second medium with respect to first medium, and that is why we have included for a given pair of optical media. So you can't change the media now because we are talking about one particular pair of media. So this is valid when for a given pair of media. You can't again, so because I am changing angle of incidence, you can't change the media because we are talking about one specific pair of media. So this is very important law, and this statement has to be written as it is. Some of the students will miss this point. Still, you may not get complete marks in your board exams if you just miss that one particular line. Right. And we'll go back to one point. So here light is actually getting deviated. We can even talk about angle of deviation. This might be useful for your Olympiad exams. Like, see, how much actually the light is getting deviated. See, this is the refracted ray, and this should be the actual path of incident ray. See, this is the actual path of incident ray. This is the actual path of incident ray. And this is a refracted ray. So the angle between actual path of incident ray and the refracted ray is angle of deviation. Angle of deviation is the angle between the actual path of incident ray and the refracted ray. So we can frame a relationship between this delta R and I by just seeing the diagram. So this whole angle is I, vertically opposite angles are equal. So I can simply say I is equal to R plus delta, and this means delta is equal to I minus R. So when light is entering from optically rarer medium to denser medium, the formula to calculate angle of deviation becomes I minus R. In the similar way, when light is entering from denser to rarer, we are now clear that this is denser and this is rarer. When light is entering from denser medium to rarer medium, Again, this should be the actual path of light. This is the actual path of light, and this is the refracted light ray. Angle between actual path of light and the refracted ray, actual path of light and the refracted ray is angle of deviation. So right, this time this will be equal to this. This is I, because this one is the straight line and this is a straight line. Vertically opposite angles are equal. So if this is I, this will be I. So this time we'll get R is equal to I plus delta. This whole R is I plus delta. From this, delta is equal to R minus I. So you can even talk about angle of deviation when light is entering from one medium to another medium. So based on whether light is entering from rarer to denser or denser to rarer, we can talk about angle of deviation. So that's all for today. Thank you everyone for being patient and listening to this class. And you can scan this QR to understand about more courses, whatever are there in our Knowledge Hub by Sri Chaitanya. Thank you so much.